Hey gang, and welcome to the Worksheet Solutions Walkthrough for Resonance Returns. More practice in choosing major, minor contributors. So if you're here, I'm assuming you know two things. One, you know what resonance is and you know how to draw it. And two, you've also watched a video where we look at how to identify, based on having many resonance hybrids, which ones might be the major contributor or the minor contributor, or you know how to rank the quality of resonance structures and how they contribute to the overall hybrid based on how charges and bonds end up when you draw resonance, okay? So you're obviously here for answers. I should stop talking. Let's do the worksheet. Okay, gang, so we have 7 resonance problems on this worksheet. So we're just gonna go one by one. I'll show you how I would draw the resonance for one letter, pause video, and then we'll tackle the next one. So let's start off with cyanate ion, okay? So remember, nothing goes out the window as far as how we draw our Lewis structures, because before we draw resonance, right, I didn't give you necessarily the Lewis structure for all of these examples, so you have to draw the Lewis structure if it's not already there, then we can go into full resonance mode. Okay, so with cyanate ion, right, let's see how many electrons we're working with. So 6, 4, 5, and then the 1 from the -1 charge. So total number of electrons, we got 10, we got 16 electrons total, okay? So I'm gonna speed things up a little bit in terms of drawing Lewis structure, because I'm assuming some of you are probably getting better at this point. So as the structure here suggests, we have a skeleton like this. And at this point, I know you all know carbon likes to make 4 bonds, so what I'm just gonna try right off the bat is just doing 2 double bonds on carbon on both sides, and then filling in both of oxygen and nitrogen's octets, because carbon not only has a full octet here, but the formal charge is 0 on carbon. 1, 2, 3, 4. That's a good spot for carbon to be in. So let me just fill in the octet for oxygen, 2, 4, 6, 8. Let me do the same for nitrogen, 2, 4, 6, 8. Let's count our total number of electrons, and if that's good, then we can do formal charges for the overall structure. So 2, 4, 6, 8, 10, 12, 14, 16. Okay, so this structure is a valid Lewis structure because we are within the bounds of our electrons. However, right, we're not done because we need to assign formal charge. So for oxygen, right, comes in from the 6th column, 6 valence electrons. Oxygen is in control of 1, 2, 3, 4, 5, 6. So oxygen is chilling with a 0 formal charge. Carbon, as we stated, comes in with 4, right? 1, 2, 3, 4. Carbon is also 4 minus 4, chilling with a 0 formal charge. Now nitrogen, 1, 2, 3, 4, 5, 6, comes in from the 5th column, so we have a 5 minus 6 situation, right? 5 valence electrons that nitrogen brings to the table, but nitrogen is in control of 6. So we have a -1 on nitrogen, which makes sense because the overall structure of cyanate ion has a -1. So this is a resonance hybrid, right? We can definitely draw resonance, we will do that, but this is a valid Lewis structure. This is one of the hybrids present for cyanate ion. So let's go ahead and do our thing. So if I can draw, you don't have, again, some teachers will be very adamant about drawing brackets around your resonance structure. If I forget to do it, don't take it personally. My first teacher, shout out Mr. Long, was big on that, and then I had professors after that weren't. So I've lost the habit a little bit. So what I can do here is I could, and I'll use a different color, I could swing these electrons in here to make a triple bond between carbon and nitrogen. And if I do nothing, then carbon will be overloaded and have 1, 2, 3, 4, 5 bonds, and that's no good. So if I make an extra bond between carbon and nitrogen, then I can dump electrons onto oxygen. And maybe you're thinking, Joe, how did you know how to do that? Here's what I was thinking. Right here, nitrogen has the negative charge. But I know that oxygen likes negativity a bit more than nitrogen. And remember our resonance rules. Fill everyone's octet, and then the second thing that we can do for ideal hybrids is place a charge where it makes the most sense to do that. So if I can move this negative charge onto oxygen, that would be the best case scenario. So let me try and do that. So again, let me draw my double-headed arrow to say, hey, look at me, I'm drawing resonance. I would have a single bond here, 3 lone pairs on oxygen, a triple bond between carbon and nitrogen with 1 lone pair on nitrogen, and now we can do formal charge, analysis. Nitrogen, 1, 2, 3, 4, 5. Now nitrogen has a 0 formal charge. I keep doing a 0 to me, but it's for the camera. Carbon still has a 1, 2, 3, 4, still sitting at 0. And it's oxygen now that has 1, 2, 3, 4, 5, 6, 7. Comes in from the 6th column with 6 valence electrons. Now it's in control of 7. Oxygen has the negative charge, which is what I was explaining. So if we're even going to preliminarily look at these resonance hybrids, this is slightly better because everyone has a full octet. Everybody has a full octet, but here, oxygen, the more electronegative atom, has the negative charge, and it handles that a little bit better than nitrogen. So these are and there's actually one more resonance structure. Let me show you it. I'm going to save myself the space of actually drawing it. I could do it from here to here. I'll draw in blue. Hopefully this isn't too confusing, but I could instead, actually let me just redraw it really quickly. If I just start over with this structure right here, I could swing this down, do basically the opposite of what I did over here, and draw my arrows like that. Fill out my brackets like a good resonance drawer. Okay, I can have this where I have a plus charge on oxygen because 1, 2, 3, 4, 5, and nitrogen 1, 2, 3, 4, 5, 6, 7, 2 minus. So you might think to yourself, well, that's crazy. We need a -1, and we still do have a -1 charge overall. Okay, obviously the plus takes 1 away from the negative. So if we have these 3 resonance structures right here, 1, 2, and 3, this is by far the worst resonance structure because we have charges on 2 atoms. You want to try to have ideally no charges, but we have to have a -1. But here we not only have 2 charges on 2 different atoms, we're forcing nitrogen to have a -2, and we're forcing oxygen that does not like positive charges to have one. So this is a big no-no. Now, the real battle is between these two, but like we discussed, it comes down to who is more comfortable with the negative charge. Is it oxygen or nitrogen? And the answer is oxygen because oxygen is more electronegative. So this is the overall, biggest major contributor to the overall hybrid. So remember, the overall resonance hybrid of cyanate ion looks like this, this, and this, but it looks like this most of the time, or that is the strongest contributor. All right, letter B. Okay, gang, so in letter B, we have a structure called formamidic acid, okay? So, if we take a look at how it's written structurally, the Lewis structure is a bit weird. So if you couldn't get this right off the bat, maybe you had to Google it, or maybe just had to watch this, that's totally fine. Do not sweat it. I wanted to pick unique examples. So it's laid out just like you'd expect it to be. So we have an OH, then we have, I'm going to use bond line, then we have this carbon up here, which only has 1 hydrogen. And usually, right, we don't draw the hydrogens, but I want to make it a point. This carbon only has 1 hydrogen, right? And it has 1 bond to oxygen. So it has to have 2 bonds somewhere. And you can see that this nitrogen has 2 hydrogens. So if the nitrogen has 4 bonds and no lone pair, that would make sense as to why it has a positive charge. So I hope you could arrive at this Lewis structure, or I hope that this Lewis structure, at least now with that reasoning, makes a little bit of sense. So I will now erase this H up here. Well, actually, what we'll do is just to prove that we are also within our electron limits, right? We have 1, 2, 4 hydrogens total, so 4 H's. So that's 4. I'll just do 4 from H's. Then we have 6 from the oxygen. Then we have 4 from the carbon. And then we have 5 from the nitrogen. And we're going to knock 1 off because of the plus charge. So 10, 14, 19, but really we should be looking at 18 electrons that we're working with, right? Because I'll say minus a +1, if you will, for the plus formal charge. So 18, okay? So if we look at this real quick, 2, 4, 6, 8, 10, 12, 14, 16, 18. We are within our limits, and I totally forgot to put a plus charge right here. Okay, so this is a valid Lewis structure. Also, one of the resonance hybrids we have here. So let me draw my brackets. Let me draw a double-headed arrow to say, hey, look at me, I'm going to draw resonance. And I'll use my green marker. One resonance move we can do is swing these electrons up on nitrogen. Now, I could just do that and then draw a separate resonance structure like this, and I'm going to do it temporarily. Nitrogen would have a lone pair, just have the one hydrogen right there. So this would deprive carbon of a bond, but it would eliminate nitrogen's positive formal charge. Now let me tell you, while this is valid, this resonance structure doesn't really even compare, because our first rule when evaluating resonance hybrids, and I will draw a different resonance structure, is make sure everyone has a full octet. Everyone has a full octet in this structure. So even though you could argue that this structure eliminates the positive charge on nitrogen, it does that at the cost of creating a situation where one atom in the structure does not have a full octet. This carbon only has 3 bonds. It only has 6 electrons in its valence. So this is right off the bat a no-no. Resonance structure won't really even compare. It won't even contribute that much, if at all. So just wanted to get that out of the way in case maybe you were thinking, oh, I generated this resonance structure and the nitrogen has no positive formal charge. Why is it not in the solution? So what I'm going to do instead is not only just bump these electrons onto nitrogen as a lone pair, I'm going to prevent that carbon from becoming electron deficient by swinging down a lone pair from oxygen. So everyone continues to have a full octet. So I'm going to just smush the HO bond together. So now we have a double bond to the carbon up top. And now we have nitrogen having a lone pair, still these 2 hydrogens right here. So as you can tell, nitrogen now, 1, 2, 3, 4, 5, has a 0 formal charge. This carbon still has a 0 formal charge, 1, 2, 3, 4 for that carbon. Now it's oxygen that has now given up the lone pair. It is now sharing it as a bond. So let me actually just do this for clarity. 1, 2, 3, 4, 5. This oxygen has now the formal charge. It's bearing the positive formal charge. So just like in our previous example in A, I think you can tell between these 2 resonance structures which one is the major contributor. It is the top structure, the first one we drew, because who is better at it's somewhat maybe the opposite logic. We know oxygen is more electronegative than nitrogen, so oxygen handles negative charges better. If you kind of reverse that thinking, oxygen loves electrons more, therefore it hates being positive more than nitrogen does. Nitrogen is like our best case scenario. It's better for nitrogen to be positive than oxygen, because oxygen loves being negative so much that being positive, big thumbs down. So this structure is better. It's better to put the positive on the nitrogen versus the oxygen. So of these 2, this structure contributes more to the overall resonance hybrid. And now on to C. Okay gang, so in letter C, and don't hold me to this name, we're going to take what is usually ethenamine, but it's the deprotonated version. So I'm just calling it ethenamine. I wanted to say anion, but couldn't find the name. I honestly didn't try that hard, but the structure's fine, just iffy on the name. However, if we take a look here, sort of similar to our last structure, kind of, but let's take a look at what we can, maybe draw as a first valid Lewis structure. So if I draw, clearly I have 2 carbons and a nitrogen and 1 hydrogen. So to make these carbons work, I have 2 H's here and 1 H here. And I clearly have no charges on either of the carbons. I have 1 on nitrogen, but we will get there. But to make this work, to make sure that these carbons have a full octet, it makes sense that I have a double bond right here, right? Because then this carbon has 1, 2, 3, 4, and this carbon up here is 1, 2, 3, 4. So the double bond between the carbons makes sense, okay? And we'll count electrons in a second. But then to give this nitrogen a negative charge, right, it needs to be in control of 6 electrons because it comes from the 5th column of the periodic table. So if I fill in the octet right here, 1, 2, 3, 4, 5, 6, that would do it to give nitrogen a negative charge. Let's make sure we are within our electron limits. So from carbon, we have we have 2 carbons. That means that's 8 electrons right there. We have 5 from nitrogen. We have 3, 4 from hydrogen. And we have 1 electron from the overall charge. So 6, 10, we have 18 total electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18. Bingo. We're good. So I'm going to erase these hydrogens right here. Okay, so quick example here, only one Lewis structure resonance structure that we can draw. And what we can do is, let me draw my brackets right here. What I can do is I can swing these electrons down here and form a nitrogen-carbon double bond, which will then give the nitrogen, a 0 formal charge. But I have to do something here, and let me draw that arrow a little bit more in between. That's kind of janky, sorry. But I will break the octet rule with this carbon if I do nothing, right? 1, 2, 3, 4, 5. What I can do is I can kick these electrons up as a lone pair on the terminal, the end carbon, okay? So what will that look like? Draw your double-headed arrow to say, hey, look at me, I've drawn resonance. Trust your arrows. Nitrogen, just the 1 hydrogen, just the 1 lone pair. And now we have a lone pair on that carbon. And if you do the formal charge math, you will see, because we have 2 hydrogens here, 1, 2, 3, 4, 5, that carbon is now what we call a carbanion, a carbon anion. And this nitrogen now is in control of 1, 2, 3, 4, 5. 0 formal charge for that nitrogen. So we have 2 resonance structures. Let me draw this a little better. So it really comes down to who handles the negative charge better, a nitrogen or a carbon. And I think you're sitting at your computer confidently clenching your fist saying, Joe, a nitrogen does. And you're absolutely right. This is the better structure if we're going to just consider these, considering these 2 and how they contribute to the overall resonance hybrid for this ethenamine anion. It is this resonance structure that contributes more than the bottom one, because nitrogen is more comfy with that negative charge than is this carbon, okay? Letter D. Okay, gang, so in letter D, we are dealing with acetonitrile oxide. Now, this Lewis structure can be a bit wacky, so if you had to check the PDF solutions to see what it looked like, don't worry about it. It's kind of weird. However, if we take a gander up here, and I also did the electron math ahead of time, because you don't need to see me do that again. While it can be strange, I want to highlight something. So with the carbons right here, we can see that this carbon right here clearly has 3 bonds to hydrogen, 3 bonds to 3 hydrogens, and 1 bond to carbon. So it's an sp3 carbon. Now, the carbon it is attached to carbon and nitrogen, 2 different atoms. That is an sp carbon. So I hope that is, I think, a nice tip for this Lewis structure, because that carbon is linear. So we have a triple bond situation on our hands. So to draw this, it's super strange, but this is going to be our CH3 right here. This carbon is going to be our sp carbon, and a first move I would do is triple bond this to nitrogen. And remember, since sp carbons have linear, because there's 2 bonding locations, right, the best way we can spread out these bonds, because of our VS EPR knowledge, is 180 degrees. So you actually have to make sure you're representing this linearly, right? You can't, this is a no-go. If you drew this on a test, people would mark it wrong, or they should mark it wrong if they don't. Anyways, right? So just by doing that, we have represented our CH3, we have represented the carbon, the sp carbon, as well as nitrogen, and the last thing we need to do to draw a valid Lewis structure, which will count as 1 resonance hybrid, is actually connecting this nitrogen to oxygen. Now, I'm just gonna go ahead, this nitrogen right here, 1, 2, 3, 4, it has a full octet with a +1 formal charge. This oxygen right here, if I just fill it in, would have a -1 formal charge, which would make sense because the overall structure is neutral, right? So this plus and this minus would cancel out, but let's double check our electron count. I have these 3 hydrogens right here. Of course, I just erased them. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. So this resonance structure, this Lewis structure, is a valid Lewis structure for acetonitrile oxide, which means it is a valid resonance hybrid. So now that we have one, let's draw the rest. So one thing I can do, I'll draw my double-headed arrow to say, hey, look at me, I'm drawing resonance, is I could swing electrons in like this and make a nitrogen-oxygen double bond, and then I could boot an electron pair up on the sp carbon. So in doing so, now I have two carbons right here, and since the lone pair is now up here, this carbon is no longer linear. It's going to be sp2. It's going to be trigonal planar. So I can actually draw this in a bent way if I, that is totally fine. However, I need to keep this perspective with nitrogen because it is still linear. So I will look like this. Nitrogen only having two bonding areas, right? So sp, it's sp hybridized. So let me make sure I did that the way I wanted to. Yes, cool. So this is a valid resonance structure. However, I need to label my formal charges. What I can do is recognize, I'll get the blue out, is nitrogen still has four single bonds, four sigma bonds that it's a part of. So nitrogen still has 1, 2, 3, 4. It still has a +1 formal charge, right? Comes in with 5, in control of 4. Carbon, right, so now oxygen, 1, 2, 3, 4, 5, 6. Neutral, that's great. Carbon, 1, 2, 3, 4, 5. Carbon is negative. Interesting, okay? So, we can do one more resonance move. And I'll not draw my arrow so obnoxiously large this time. As crazy as it sounds, gang, what we can do is we can actually swing in electrons from oxygen yet again, and then I can boot yet another pair of electrons onto carbon. And if you're cringing at your computer, you're absolutely cringing for the right reasons. This is going to look super weird. We'd have two lone pairs on carbon. We'd have just the single bond from carbon to nitrogen, and then we have a triple bond between nitrogen and oxygen, and we need to now assign formal charges. Lewis dot structure-wise, this works, but I think formal charge-wise, you're going to see it's not that great. So oxygen actually is a +1 formal charge here. 1, 2, 3, 4, 5. 6 minus 5 +1. Nitrogen has a +1 because it still has 4 single bonds, and it's carbon here, 1, 2, 3, 4, 5, 6, that has a 2- charge, or -2, however you want to represent it. So overall, right, we are neutral. Overall, we're neutral, but you can see a few things wrong with this. One, why would we ever put a 2- charge on a carbon? Carbon's not that electronegative. That's one. We have 2 electronegative atoms that are positive. That's not great. And we have 2 like charges on the same atoms next to each other, right? Like charges do not attract. Like charges repel. So this is wrong for a few reasons, and this is wrong because it's not that electronegative. So this structure overall is bad news bears. Just awful. Really bad. Probably doesn't, while it's theoretically possible, probably does not at all contribute to the overall hybrid. This structure up here, it does, so let me put it this way, gang. We're considering these two structures right here. We really have a situation where oxygen, the electronegative atom, the most electronegative atom in the structure overall, has the negative charge. Nitrogen, a plus charge, and then moving down here, we have the same positive charge on nitrogen, but in comparison, right, we have carbon bearing the negative formal charge down there. Clearly, I think you're all, waiting for me to say it's this structure up top that is the major contributor to the overall resonance hybrid. Because, while it's not amazing that nitrogen has a positive charge, we can't avoid it, and these charges, right, are next door to each other. So they are going to have some electrostatic interaction, right, a plus and minus, opposite attract type thing. This is clearly better. Oxygen's more fit to handle the negative charge than carbon. This is just a whole bunch of wrong down there. So this really isn't feasible at all, okay? So, probably spent too much time in that, but on to the next letter. Okay, gang, 3 more, stick with me. So, in letter E, we're gonna look at chlorite. And while it is kind of a, simple example, I think it's kind of cool, and I think you'll see why. So, if we look at chlorite, ClO2, skeletal structure looks like this, right? Chlorine's in the middle, and we have 2 oxygens. So, and I'm gonna give myself a little bit more room before I pigeonhole myself. I have nowhere to draw. Okay, so did the math ahead of time, right? We get 7 electrons from chlorine, 12 because of 2 oxygens, and then 1 from the overall minus charge. So we have 20 electrons to work with. So let's go ahead and fill everyone's octet. So what I can go ahead and do, I have to bond these together, because the thing is we are working with all electronegative atoms right here, right? No one involved here is a giant fan of positive charges. If anything, we're a fan of negative charges. So if we take a look here, if I went ahead and just filled everyone's octets, let's evaluate, are we in our electron range and whatnot? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So the answer is yes. We just drew a valid Lewis structure. So let's look at some formal charges. So, oxygen, -1, oxygen, -1. So remember, chlorine comes from the 7th column. So we haven't really typically done formal charges for halogens. So let's see what that looks like. 1, 2, 3, 4, 5, 6. Chlorine with the +1. And overall, right, 2 minus, 1 plus, that gives us a -1 overall. This is a valid Lewis structure, resonance hybrid, resonance structure. So, let me go ahead and put in brackets. And again, I really should be putting a minus up here. Don't roast me for not doing it. But we can do better than this, okay? So, because chlorine's not loving that positive charge. And now the thing is, and here's why I like this example, is that chlorine is in the 3rd row of the periodic table. Of course, I should have known that right off the top of my head. It is 3rd row, I believe, down to the point where it can expand its octet. Chlorine is just not limited to having 4 bonds or 8 valence electrons, or I guess I should say it has the 3D subshell to shove electrons into an empty 3D. So what we can do is I can actually swing electrons in like this. So this resonance structure, right, I'll only have 2 lone pairs. I'll have a double bond. I will have my chlorine. I will have 1 lone pair. I will have 2 lone pairs, sorry. I don't know why that was so mind-boggling for me to accept. All I changed was swinging electrons in, and now I have a double bond between oxygen and chlorine. So now, let's reevaluate formal charges. So this oxygen is now neutral. 2, 4, 5, and 6. Neutral. Now let's look at chlorine. 1, 2, 3, 4, 5, 6, 7. Chlorine's neutral. 1, 2, 3, 4, 5, 6, 7. -1 on oxygen. So if you can see, just by sharing, not only did we eliminate 2 charges, but we eliminated that really unfavorable positive charge on chlorine. So this is definitely a step up in resonance world, right? Everyone has a full octet, and chlorine's fine because it can expand its octet. And we have a negative charge on an atom that's very equipped to handle a negative charge, okay? So, can we draw any more resonance? The answer is yes. So, if I draw my double-headed arrow, and you might think, and again, this was a hard thing for me to accept as well, because we have symmetry here, so technically these are the same, but I could go ahead and reverse that resonance move. I could swing these electrons in. I could bounce these ones out. So what I could do with that is, yep, I'll do that first. I just thinking of the order in which I wanted to do this. So really, these two, they're the same, but they're different because, there are 2 oxygens, even though they're symmetrical, right? So you can almost think of these oxygens kind of sharing the charge in a way. But basically, we have the ability to draw the resonance structure 2 different, the same resonance structure twice, right? And there is one more resonance structure I do want to show you. We could, and I'm not going to draw the arrows to appropriately do it, but we could have this resonance structure as well, where the negative charge is 1, 2, 3, 4, 5, 6, 7, 8 on chlorine. Okay? So, we have a few options here, and overall, I believe these structures right here, since oxygen is more electronegative than chlorine, these 2 structures, since they are equivalent, right, but they are 2 different independent structures, even though we have the resonance structure here that gives, neutral formal charges to oxygen and a -1 to chlorine, we have these 2 right here that have neutral chlorine versus the chlorine that's positive. This is the worst resonance structure. I would say this comes in second place, and then these two are tied for first because we have full octets, minimized charges, and given the negative charge we couldn't avoid to the best atom to, the atom most equipped to handle it. Okay, on to the next letter. Okay, gang, so an F, right? Finally, I've given you the Lewis structure, so you're like, I guess I should say, it's bond line, so there's no, deducing what the Lewis structure is. It's just kind of, here we go, drawing resonance right off the bat. Okay, so if we take a look here, we can just go ahead and draw some double-headed arrow. And one resonance move we can make here is we could swing these electrons down into a carbon-carbon double bond, and if we do nothing, we're in trouble because we would break the octet rule at this carbon right here. So what we can actually do is bounce this lone pair up to double bond up to a lone pair on that carbon. So let's evaluate that. So I now have a double bond right, kind of drew that weird. There we go. Double bond right there. Lone pair on this carbon. I'm going to try and squeeze it in nicely. And now I have this ether, this OCH3, right? And we have a minus charge on this carbon right here. Okay? And what I'm going to do is I'm actually going to redraw the structure down here because I want to show you one more Lewis structure before we go all analytical resonance contributor hybrid wise. Okay? So one other thing we can do, wait, let me make sure I'm not just making things up. Oh, yeah. One other thing we can technically do is I could swing these electrons from the oxygen down here to make a double bond, and then I could bounce the lone pair up here as the double bond as a lone pair right there. I can't refer to things properly. We could technically do this. So that gives oxygen a positive charge because there's a bond to carbon right there. So 1, 2, 3, 4, 5. Now we have a double bond there. We have a lone pair here and a lone pair there. So we have 2 minus charges, and I hope by the time I was even finished drawing that, you cringed. So let's take a look. So we have, these are the same. These are 2 different. So let's start with the worst. This down here, I questioned if I should even draw it, but I'm hoping you're seeing a few things. One, we put a positive charge on oxygen. Oxygen's not a fan. But even more egregiously than that, I even waited to mention the worst part, is in doing that resonance move, we produced another carbanion, another carbon with a negative charge, but we produced it right next to an already existing carbanion. We have a negative next door neighbor thing going on here. I almost said opposites attract. Same charges repel. This structure sucks. It's terrible. It won't even contribute. It's that bad, right? We made oxygen worse off, and we put 2 charges next door to each other that will repel. So we just increased the overall energy of that structure by a lot. Okay? So just wanted to point that out. As much as I like to show you good examples, I want to show you, sometimes we're evaluating things in the moment on a test or whatever, and it's easy to just produce another option, and we need to think about how we can easily rule that out. So up top, this versus this as far as our battle for best overall contributor to the resonance hybrid. Let me make this a little bit nicer. So the reason why this structure is better for the overall resonance hybrid, and let me just erase the, we'll leave it there. We have the option of putting the negative charge on this carbon or this carbon. So it's a carbon either way, okay? Can't avoid that. However, so oxygen is an electronegative atom, right? It is going to be, any bond that it's part of, it's going to be stealing more electron density from whoever it's bonded to. So if we take a look here, you could just assume that this oxygen is already delta minus. It's more partially negative than a typical atom. Well, what did we do in this resonance move but put a negative charge next to an atom that's already partially negative? So it's the same deal down here, but just not as bad. We basically created a negative charge on an atom next door to an atom that's already a hub of negative charge. So right here we have the same charge repulsion thing going on here, but we don't have that here. It's not as bad. If anything, this oxygen is going to be sucking electron density out of these this atom, but maybe even this atom a little bit. So this negative charge is sitting pretty. So I like this example because it's simple, but it's not so in your face as to why this is the better structure and it contributes more to the overall resonance hybrid. Okay? Gang, I know this has been a longer video, but one more, just stick with me. Come on, one more, you got it. Okay, gang, to round out this resonance, hybrid, contributor, major, to some combination of those words, worksheet, we look to an old friend, bicarbonate, okay? So I'm gonna, I've done the electron math over here. The video is already as long as it is. I'm just gonna kind of skip to the first structure, draw the resonance, explain, the major contributor. We'll call it a video. Okay, so carbon's the central atom here. So bicarbonate, this is by no means the last time you will run into bicarbonate in your chemistry career, or maybe you've already, had a soiree with bicarbonate in jOeCHEM. But carbon is the central atom here. We have 3 oxygens. So I'm just going to go ahead and draw one Lewis structure, fill in. I'll show you the electron math and why it checks, that it checks out. So we need an overall negative charge here as well. So if you're already eyeing up that 1 oxygen with the 3 lone pairs, then for good reason you are. So we have 24 electrons to work with. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, and then 24 for that oxygen-hydrogen bond. We are sitting pretty at 24. Where's the negative charge, right? What's this oxygen up here? 2, 4, 6, and then 7 from this bond, minus 1 charge. Okay, so if we are to draw resonance, and I'll stick with my brackets, okay? Remember, whatever your teacher, whatever, it's their world. We're living in it, right? So brackets if you need them, no brackets if you don't. So what can we do here? Well, one easy move would be to form a double bond right here. Let me actually just use my green. We can form a double bond here, carbon-oxygen. If we do nothing, we'll break the octet rule. So what we can do is we can bounce an electron pair up to that oxygen right there. So, trusting my arrows and drawing the results of that electron move, I now have a double bond down there, just 2 lone pairs. I now have a single bond and 3 lone pairs right here and a minus charge. And I didn't touch this OH down here, so it is just hanging out, chilling, like a villain. Okay, so I hope you can see, that's all the resonance we can draw, by the way. If we're taking a look, they're the same. And, these are 2 resonance structures. They are 2, and they're symmetrical. So they both contribute to the overall resonance hybrid. These are the only 2 we have. Since they are the same, they contribute equally. So if we will circle, if we're going on with our circling, they both contribute. And sometimes this is a very popular example to have this asked with, same with ozone. If you needed to kind of draw it, these bonds, since, it's a single here and a double here, and a double here and a single here, you can almost think of them as not just a single and a double, same here, but more of a 1.5 bond. So very typically you will see bicarbonate drawn like this. Just to show that basically that the resonance here, right, the overall hybrid, there's a single here, a double here, so if they're contributing equally, 1 plus 2 divided by 2 is 1.5. So here and at this location and at this location, they're more 1.5 bonds than a single or a double. Gang, I know this was long. I hope that if you were seeking some explanation here for some of these examples, I really tried to pick unique ones that, in terms of the Lewis structures and the resonance produced, that you got the answers you were looking for. If you're watching this video, that means you've thrown me some money and you've supported jOeCHEM, and I for real cannot thank you enough. No one has to watch these videos, but I'm glad you are. I'm glad you're taking me along and choosing jOeCHEM for your organic chemistry journey, and I hope it's, propelling you to success. And I hope I'm here now, and I hope you're using jOeCHEM to the end of OCHEM, to the end of organic chemistry, and I hope to see you all in the next video.